have a bound state. In particular, the binding energy epsilon b, here positive, of the two fermions is related to the two-dimensional scattering length by the equation 15. And you see again in the formula appears this gamma, that is the Euler-Mascheroni constant. And you see what is relevant is that the binding energy scales as the inverse of the scattering length squared. Moreover, the attractive negative interaction strength G of the S-wave pairing is related to the binding energy by equation 16. You see there is a formula that relates the strength G of the contact interaction to the binding energy. To study the two-dimensional BCS-BC crossover, we have adopted the formalism of functional integration. The partition function Z of the uniform system with fermionic field psi at temperature capital T in a two-dimensional volume L squared and with chemical potential mu is given by equation 16. And is written as usually as a path integral where it appears the Euclidean action capital S that is given by equation 18 and equation 19. In the equation 18 there is the Euclidean Lagrangian formally, and in the equation 19 there is the explicit expression for this Euclidean Lagrangian density. And you see there is the strength G of the coupling between fermions with opposite spin. We are in particular interested in the ground potential, capital omega, that can be related to the partition function by this formula, namely the ground potential is simply minus 1 over beta. Beta, remember obviously is 1 over the absolute temperature T, and then the logarithm of the partition function. Now, in general, here we are working at the one loop level, namely we include mean field plus Gaussian fluctuations. And the ground potential will be the sum of two contributions, the mean field one and the one due to the Gaussian fluctuation. The mean field one is simply obtained introducing the pairing field after a Haber-Stratonovich transformation, but then putting this pairing field equal to a constant in space and time. And in this way, you simply get the mean field partition function. Instead, the partition function for the Gaussian fluctuation is more complicated because you have to do a quadratic expansion of the pairing field around the uniform contribution that is this delta naught. So the procedure is quite complicated. I only show the main results. In particular, after functional integration over the quadratic fields, one finds that the mean field ground potential is given by equation 23, and you see it appears the energy gap delta naught squared divided by the strength G. And there is also an expression here which involves this capital ESP, that is the spectrum of fermionic single particle excitations, which gives a zero temperature contribution, but also a finite temperature contribution. And this is equation 24 for the spectrum of fermionic single particle excitation. It's quite familiar in the BCS theory. The Gaussian ground potential is instead much more complicated and is given by equation 26, and it's related to this capital M that is the inverse propagator of Gaussian fluctuational pairs and must be in general calculated numerically. Well, in the BEC regime of the BCS-BC crossover, one can get an approximate expression for the Gaussian ground potential that is given by equation 26. And you recognize that there is this E sub index called that are the collective bosonic excitation spectrum, where the frequency omega q must be, however, obtained setting the determinant of the inverse matrix, inverse propagator of Gaussian fluctuation equal to 0. However, the formula for the ground potential is quite, let's say, formally simple, because you recognize again the 0-point contribution to the elementary bosonic elementary excitation. It is again formally divergent, but can be regularized, plus the thermal contribution, that is the familiar one of bosonic, let's say, particle, in this case, quasi-particle. At zero temperature, we can compare our theory, that is, well, you see, in the plot, we have the dashed line, that is a constant. You see, here I have the pressure at zero temperature as a function of the logarithm of the binding energy. On the left side, you have the BCS regime. On the right side, you have the BEC regime. And if you consider only the mean field contribution, the pressure, here the pressure unit in units of the ideal pressure, of the pressure of an ideal Fermi gas is 1. It remains 1 in the crossover. So at the mean field level, the pressure is constant. Does not depend on the interaction. And so you see, it's really crucial, the inclusion of Gaussian fluctuation here. And the Gaussian fluctuation, our theory with Gaussian fluctuation is instead the solid black line. And instead, the red dots are the circles, let's say, fillet circles with the arrow bars are the experimental data of a paper published some years ago. And you see, there is a very, I would say, very good agreement between our theory and the experimental data. But you see, it's truly crucial to include the quantum, say, the beyond mean field Gaussian fluctuations to have a good comparison with the experiments. At finite temperature, the calculation is more complicated, and if you want to study the sound modes, you need, as I showed previously, also the superfluid density of the system. And at the Gaussian level, NS, our superfluid density, depends only on the fermionics single particle excitation. This can be proved. However, beyond the Gaussian level, also bosonic collective excitation contribute. And this can be seen in this paper of Lara Benfatto and co-workers. And taking into account that somehow the beyond the Gaussian level contribution of bosonic collective excitations, we write somehow heuristically the superfluid density as the total density and minus the contribution of the normal density. And here the contribution of the normal density is the sum of two contributions. The contribution to the normal density of the single particle fermionic excitation, and the contribution to the normal density due to instead the bosonic collective excitations. You see, there is a plus here and minus here because the E sub index SP are single particle and are fermionic, while E sub index CO are bosonic collective. Okay. Again, the superfluid density given by this equation 29 is the bare superfluid density if you want to take into account also the formation of quantized velocities, and must be renormalized to get the renormalized superfluid density. And again, one can use the Kosterlitz-Thouless Nelson renormalization group equations. We have calculated the critical temperature of the Brzezinski-Kosterlitz-Thouless as a function of the crossover, in particular here as a function of the logarithm of the binding energy divided by Fermi energy, the Fermi energy of non-interacting fermions. And again, on the left, you have the BCS regime, while on the right, you have the BC regime. The solid curve is the one obtained taking into account both bosonic and fermionic elementary excitations. Instead, if you consider only the fermionic elementary excitation, you see that you have this dashed line, and which is quite good, let's say, on the left side, namely the BCS regime, but it goes to a constant in the BC regime. Instead, if you include also the Gaussian fluctuation, as shown in the solid black line, the Brzezinski-Kosterlitz-Thouless critical temperature diminishes by increasing the binding energy, and actually it goes logarithmically to zero if the strength the binding energy is extremely large. And again, here we have some experimental data obtained in a physical regulators paper in 2015, and you see there is a relatively good agreement on the right side, let's say, and in the you see the experimental data somehow are, from my point of view, not completely clear, because they exceed this value of about 0.13, and from my point of view, it's quite difficult to understand theoretically why there are these experimental data. It's 3 points here. However, I will say that again, the inclusion of Gaussian fluctuation is crucial to get a relatively good comparison with the experimental data. However, we are interested also in the sound modes, and also in this case, we calculate the first sound velocity U1 and the second sound velocity U2, knowing the equation of state and the superfluid fraction. We also analyzed the amplitude modes W1 and W2 of the response to a density perturbation. So if you consider a uniform system and you perturb the density with a weak perturbation, this delta n as a function of space and time, you have two contributions to the perturbation. One, you see, where you have a wave that propagates with velocity u1, and another, let's say, wave that propagates with velocity u2. And in general, the density at defined time and at some position depends on both contributions. And W1 and W2 are the amplitude of this contribution. In general, I anticipate that in our case, we see that W1 is it's always very close to 1, while W2 is very, very small. So it means that if you perturb with a density perturbation your uniform system, you are mainly exciting the first sound. And to excite also the second sound, you need some other technique. Okay, here there are the results.
Do you also hear that sound?
Sorry?
There is a strange sound at the moment, but you don't hear it.
Yeah, well, I see. I heard something, but now it seems better.
Okay.
Can I continue?
I guess so. Maybe let me just check with the technique if there is anything going wrong.